Okay, lecture 4 for statistics for decision making, we're going to talk about levels of measurement. Now, before we get started, remember that in lecture 3 we talked about sampling, and there's just a couple of closing comments I want to make about sampling before we move on. Okay, so number 1 is the idea of sampling with replacement or without replacement. Okay, so theoretically, when you do a sample, let's just say, for instance, that you have 100 people and you're going to take a sample of 10. Okay, then let's say that you do a simple random sample, so you just draw 10 names out of a hat. Okay, theoretically you're supposed to put each name back after drawing it. Okay, and here's the reason why. Let's say you have 100 names in the hat, and the first name you draw out is Sarah. Okay? If you put Sarah's name on the table, now there's only 99 names in the hat. And if you draw a second name, then it's technically not random anymore out of 100, is it? I mean, if you were doing it truly randomly, then it would be possible to draw Sarah's name twice. According to the laws of randomness, that should be a possibility. So listen to what I'm saying. Theoretically, you should sample with replacement, meaning that you could sample the same person twice. Realistically, that is almost never done. Okay, and here's the reason why it's almost never done, and then I'll tell you the reason why that's usually okay. The reason why sampling is almost never done with replacement is because people don't want to sample the same person twice. If you're going to sample 10 out of 100 people, then you want to actually get 10 people. And what if the odds of this happening are so small, but it is technically possible. What if you sampled with replacement, meaning after drawing a name, you then put that name back into the hat? You could technically draw Sarah's name 10 times. And then how big is your sample in that case? It's really just a sample of 1, right? And people don't want that to happen. So once they draw Sarah's name, they leave it out of the hat. That way they make sure that they're drawing 10 different people, and so they'll actually have a sample size of 10. Okay? But like I said at the beginning, though, that technically violates the laws of randomness. So why is it okay? So I just discussed why people do it that way, why they want to. But now let me say why that's okay. The reason why that's okay is because populations are usually very big. Let's say there's 1 million people in the population, and you're going to sample 1,000 people. Let's say you draw the name Sarah out of those 1 million. If you did put Sarah's name back into the hat, what would be the chances of drawing her name again? It would be really small, right? I mean, each time it would just be a chance of 1 out of 1 million. So it's almost certain that you would not draw her name again. And so that's why it is mathematically, let's just say this phrase, it is close enough to leave her name out so that you don't draw her again, because you most likely would not have drawn her again anyways. You see what I'm saying? Even if you're sampling 100 out of, even if you're sampling 10 out of 100 people, if you did put the names back into the hat, there's only, a 10% chance of drawing it again, which is pretty small on each additional draw. Okay, so in a perfect world, you would sample with replacement. In the real world, you sample without replacement so that you don't draw the same person twice. And that is mathematically okay because the chances of having drawn the same person twice would have been very small anyways. Okay, something else I want to mention before we move on are things you have to be careful about when doing samples. And that are sampling errors, non-sampling errors, and sampling biases. Okay, a sampling error is, for instance, an example would be taking too small of a sample. If you had 1 million people in the population and you sampled 10 people, that would not be statistically useful because it's just too small of a sample to tell you anything useful. Okay? That would be a sampling error. A non-sampling error would be, for instance, if you had a counting device that was defective. Okay? There's nothing wrong with your actual sample, but there still would be errors in the data. So that would be a non-sampling error. And the third thing to be careful about is a sampling bias. That's when you skew your sample, usually unintentionally, but maybe intentionally. The classic example is this. Let's say you're doing a poll on who are people going to vote for president. And let's say you're going to sample 5,000 people. So you take out a phone book and you look up 5,000 phone numbers and you call those people. Okay? That would not be a good way of doing a sample. It used to be better, but nowadays it would be horrible. And what's the reason why? Almost nobody has a landline, it seems, anymore. So they're not going to show up in the phone book. The phone book doesn't have cell phone numbers. Okay? So if you could sample 5,000 people, that's a big sample, so that's not a problem there. But you would only be sampling people who had landlines, which is a very, very specific segment of the population. So your sample would not accurately reflect the population at large. That's called a sampling bias. Okay, here's another example of a sampling bias. If you want to know how popular basketball is among Americans, so you went down to the basketball gym and you asked 500 people there, do you like basketball or not? Okay, that's going to be a very biased sample because you're going to the place where people go to play basketball. To ask them, do you like basketball? You're going to get a very abnormally high rate of people who like basketball because you have a biased sample. Okay, so those are some things to be careful about. It mentions them in the book, and you should be reading the book, and I am assuming that you're reading the book. If you don't, you're missing out on some important stuff. Okay, the lectures are meant to go along with reading the book. And what I'm talking about right here about replacement and non-replacement and errors and biases, this is all on page 17 and 18. Okay, but what we want to do now is we want to move on to section, we're going to skip this little part that you might find on page, I think, 20, called variation in data. We'll come back to variation later. I want to go to section 1.3 and do levels of measurement. Okay, so let's start the written notes here. Different levels of measurement. This doesn't necessarily mean levels like getting better and better. One's better than the other. It's just 4 different kinds. Okay? And in certain situations, one might be better than another. Okay? So the first kind is called a nominal scale level. Okay? And these are the kind of measurements you do when you have categorical data, or what's the word I said we're going to use in place of categorical? Qualitative data. Okay? Where there's no ranking of one thing is better than another. Okay? So this is for, here, let me write it this way. This is when the data is qualitative okay, and there is no ordering necessary. So a perfect example of this would be you're going to walk around the university campus and collect data on people's hair color. Okay, so you would just have categories: blonde, black, brown, red, and what else? Maybe other. Okay, and there is no ordering there. It's not like one of those is better than the other or anything like that. It's just 4 or 5 different categories. Okay. Okay, another level of measurement is called the ordinal scale level. And that's when the data is qualitative, but there is an ordering. And at first it might be hard to think of an example, but I'll give you an example. It's not hard once you're pointed in the right direction. Okay, so an example of that would be you're going to do a survey of people's favorite restaurant in town, and you ask everybody for their top 5 restaurants, ranked from 1 to 5. Okay? Now those are numbers, 1, 2, 3, 4, 5, but it's not quantitative data, it's qualitative, because you're using the numbers 1, 2, 3, 4, 5 to just mark categories: favorite, next favorite, middle favorite, second to last, and last. It's just 5 categories, and we usually number those 1, 2, 3, 4, 5. Because it's categories, it's qualitative data, but there is an ordering there. You put your favorite restaurant as number 1, and then your next favorite is number 2, and so on. Okay? All right, 2 more. The next type of measurement is to do an interval scale level of measurement. Okay. Okay, so what is interval scale level? It's like an ordinal scale level, except the difference here is that you can actually measure differences between data. Okay? So I'm going to write when we can actually measure differences between data. There's more. but there is no starting point. Okay, so first of all, I want to deal with two things there. I want to make sure you understand why that's not ordinal scale level. Because for ordinal scale level, you might say, well, can't you measure the differences there? Like the example I gave of name your top 5 favorite restaurants. And you might say, well, so you can measure the difference between your favorite and your least favorite. But here's the thing where I say you can't. Let's just pick my favorite 2 restaurants, and so I label them number 1 and number 2. Okay? That doesn't tell you how much more I like the number 1 restaurant than the number 2 restaurant. I could just barely like it a tiny bit more, or I could like it a huge bit more. The fact that they're just number 1 and number 2 does not tell you how much of a difference there is between them. On an interval scale, you can actually measure the differences. A perfect example of interval scale would be temperatures. Okay? But now let's deal with the second part. Oh, by the way, why are temperatures good? Because you can measure the difference between them, right? The difference between 80 degrees and 20 degrees is 60 degrees. You see what I'm saying? Okay, but there's no starting point. What does that mean? There's no such thing as a smallest temperature. Uh-oh, I better deal with that. If you've taken science classes, you may have heard that there is this concept called absolute zero. Okay? But the thing is, that is a theoretical concept that's never actually been achieved. So for right now, let's take that idea off the table. Okay, there is such thing as a zero temperature, but you can still go lower, right? There's -1 degrees, -2 degrees. Okay, you see what I'm saying? That's what I mean by no starting point. And the only problem with that is you can't measure ratios. Like, let's say this. Let's say again, 20 degrees versus 80 degrees. You will very, very commonly hear people say, well, 80 degrees is 4 times as hot as 20 degrees. Makes sense, right? But it's technically not true. The number 80 is 4 times the number 20. But if you were to say 80 degrees is 4 times as hot as 20 degrees, that would mean that something that's 80 degrees has 4 times as much heat as something that's 20. And the problem with that is you would have to ask this question, relative to what? Relative to 0 would be the answer, but the problem is, in an interval scale, there is no starting point. And in the temperature scale, 0's not the starting point, because you can go lower than 0. You see what I'm saying? If you said 80 is 4 times as hot as 20, that's only measured from the starting point of 0. Measuring from the starting point of -10, 80 would no longer be 4 times as much as 20, because the distance from -10 to 80 would be 90, and the distance from -10 to 20 would be 30. So starting at -10, 80 would be 3 times as much as 20. It can be very confusing, I know, and that's because you're trained to think of 0 as being the starting point. But that's not always the case, and for temperature scales, 0 is not the starting point because you can go lower. All right? And so we have the 4th kind of interval scale. The 4th kind of measurement scale, which is ratio. scale level. And that's just like interval scale, except you have a starting point, okay, a point which you could call the 0 point, okay. This is like interval scale, except there is a starting point. Okay, so an example of this would be, let's just use Celsius temperature, okay, the centigrade scale. So you hopefully know that 0 degrees Celsius is the freezing point of water. So if you were measuring the temperature using the Celsius scale, that would be interval scale. But if you were measuring temperature above freezing, then you're putting a starting point on there, saying freezing is the starting point. Okay? And if you're measuring temperature above freezing, then you can say 80 is 4 times as much as 20. Or you could do the ratio 80 over 20, which would be 4. Or 20 over 80, which would be 1/4. If you said temperature above freezing. Okay? If you just said temperature with no relative starting point, then ratios wouldn't make any sense. That would be an interval scale. So those are the 4 levels of measurement. Okay, now I want to talk about something else. Frequency versus relative frequency versus cumulative relative frequency. Okay, let me write those down. Okay, so when you're collecting data, the frequency of a certain data point is how many times does that data point come up. Okay, let me write that down. The frequency of a data point we're going to do an example of all 3 of these, and it'll seem pretty straightforward once you actually see it written out. Okay, the frequency of a data point is how many times that data point is recorded. Okay. The relative frequency is something a little different. The relative frequency of a data point is how many times that data point is recorded has a ratio of how many recordings are made. You'll see in a minute what I mean by that when I do an example. Okay, and the third definition is cumulative relative frequency. The words are getting longer as we go. Okay, the cumulative relative frequency of a data point is the relative frequency of the data points equal to or less than that data point. Okay, so we're going to do an example here. Okay, we are going to try to get an idea of how many hours students work, and we're going to do a sample of 20 students, and we're going to write down how many hours they work per day. Okay, let me scroll down here and get some space, and here's our example. We ask 20 students how many hours they work per day. Okay, we record the following data. Okay, and I'm just going to write these out. 5, 6, 3, 3, 2, 4, 7, 5, 2, 3, 5, 6, 5, 4, 4, 3. I'm running out of room, so I'm going to put the rest in front. I lost my place though. 5, 2, 5, and 3. Let me count those, make sure I got all 20. Okay, good. So there's all 20. Okay, so here's what we're going to do. We're going to make a table of the data. And there's no sense really in making 20 rows in the table because look, a lot of the numbers show up multiple times, right? Like, look at the number 2s. There's 3 of them. I don't need to make 3 rows in my table and write 2 in each row. Why don't I just write 2 one time and say that it showed up 3 times? You see, it'll save me a lot of space and time. So here's what I'm going to write. I'm going to write data value in the first column. I'm going to write frequency in the second column. And for right now, let's just stop right there, okay, just to show you how this works. This is what you would call a frequency table. I'm not going to need 20 rows. I'm not sure how many I'll need. So let me just draw that many for now. Okay, so here's what I do. I'm going to go in order. That makes sense. Okay, you see there's no ones or zeros, right? The smallest is a 2, so we put 2 here. Okay, how many 2s are there? There's a 2 there, and a 2 there, and a 2 there. There's 3 2s. So rather than writing 3 rows, 2, 2, 2, I just write 1 row for the data value 2, and I say that it had a frequency of 3. That tells anybody looking at this table that there were 3 people who said that they worked 2 hours a day. Okay? What's next? 3. How many are there? 1, 2, 3, 4, 5. So it has a frequency of 5. That data point, you see, 3 is called a data point. And there were 5 data points of 3. So I say the data point of 3 had a frequency of 5. Okay? And then next is 4. How many of those do you see there? Go ahead and count them yourself. There's 3 of them, right? So that has a frequency of 3. And then there's 5. How many 5s? There's a lot of them. I'm seeing 6 of them. And then there's 6. How many 6s do you see? There's just 2. Okay? That's what's called a frequency table. It's a way of recording 20 numbers without having to actually write down all 20 of them. I only had to write down 5 of them because there was only 5 different numbers. And then for each one, I write down how many times that data point came up. Okay, so that's frequency. Now, let's add a column on there and do relative frequency. So here's the idea. Okay, look at the frequency. I said the data value of 2 showed up 3 times. So that's interesting, right? But is 3 a significantly large number? Well, it all depends upon how many people I surveyed. If it's 3 out of 1,000, then that's very insignificant. If it's 3 out of 10, then that's pretty significant. So the frequency is important, but what's even more important is the relationship between the frequency and how many people were surveyed. And that is called relative frequency. Instead of just writing there were 3 2s, I say there were 3 out of 20. So I write this for the relative frequency. That's more informative. Because now you see not just there were 3 people that worked 2 hours, but 3 out of 20. So it gives you a better idea of, you know, what proportion of the sample said 2 hours. Okay, and for the data value of 3, which had a frequency of 5, I would write 5 out of 20. You see how that works? Basically, it's just the frequency divided by the sample size. And that number there, for instance, 6 out of 20 can be reduced to 3 out of 10, right? But I don't do that because I want to maintain the indication that there were 20 people sampled. Oh, shoot, I'm sorry. I didn't realize this. I left a number off. There was one person that worked 7 hours a day, and I just totally ignored them. Let me add that on. to the table, it was one person, and that's 1 out of 20. That works 7 hours a day. Now, for relative frequencies, sometimes people like to write those as a decimal so that you get an idea for the percentage. Okay, so for 3 out of 20, you might see that written as 0.15, so that you get an idea that that's 15%. 5 out of 20, you might see written as 0.25, so that you see that that's 25%. Okay, they're both correct. And it's not a matter of do you like fractions or decimals, it's a matter of do you want to see the information as a ratio or do you want to see it as a percentage? Okay? And then the last kind I told you about was cumulative relative frequency. That's the relative frequency of anything less than or equal to that data point. So for the smallest data point, that's going to be the same thing as the relative frequency. It'll be 3 out of 20 or 0.15 or 15%. Okay, but now for the second one, the data point is 3, and what you ask yourself is, what's the relative frequency of all of the data points less than or equal to 3? Okay, so that means 2s and 3s. How many 2s and 3s are there? There's 8 of them. So we would write 8 out of 20, which is the same thing as 0.4 or 40%. Okay? What's the cumulative relative frequency for the data value 4? How many data values are there less than or equal to 4? So that means how many 2s, 3s, and 4s together? There is 11 of them. Right? 3, 5, and 3 adds up to 11. So you would say the cumulative relative frequency of 4 is 11 out of 20, which equals 0.55 or 55%. Okay, you get the idea? You could probably fill in the rest of the table now. I'll go ahead and just fill in the numbers. For 5, that would be 17 out of 20, which is the same as the decimal 0.85, which is the same as 85%. For 6, the cumulative relative frequency is 19 out of 20, which is the same as the decimal 0.95 or 95%. And for 7, the cumulative relative frequency is guaranteed to be 20 out of 20 because that's the highest data point. And so when you count the data points equal to or less than that, you're going to end up counting all of the data points. As a decimal, that's 1. As a percent, that's 100%. Okay? Couple of things to keep in mind. When you do frequency, that column should add up. Let me write this. Should add up to the sample size. If not, then you have miscounted something. In this case, 3, 5, 3, 6, 2, 1, those add up to 20, which is our sample size. Okay? If you do relative frequency, those should add up to 1. 3/20 plus 5/20 plus 3/20 plus 6/20 plus 2/20 plus 1/20 is 20/20, which is 1. Or if you're doing the decimals, 0.15 plus 0.25 plus 0.15 plus 0.30 plus 0.1 plus 0.05, that adds up to 1.00. Okay? If you're doing cumulative relative frequency, then the numbers there should be increasing all the time. Every one should be bigger than the one above it. Okay? And the last one should equal 1. So just a couple of things to keep in mind, and that way you can just check that, and if that doesn't happen, then you know you miscounted something. Okay? That's all for today, and I'm looking forward to the future, hopefully not too far down, where we've learned all of the terminology and we can actually start doing some statistics. Have a good afternoon.